I will collect that survey in just a minute, so just hang on to it. And I will be passing out your quizzes in just a minute as well. I do want to take a look at the board over here for assignments that are coming up. So since what we're working on right now is more math involved, it's going to take us a little bit longer to get through it. So we're still looking at, there we go, section 3.1 and 3.2. I neglected to assign prepare to learn 3A, so that is now due tomorrow night. And then there are 2 homework assignments. Homework 5 is part of chapter 2, but that is for the naming of the covalent compounds. And we're not going to deal a lot with covalent compounds, so I'm going to give you a while to do that. So that is due next Tuesday, the 12th. And then homework 6 is related to the stuff that we're working on now, which is relevant to lab and we're going to be sticking with. So I want you to work on that for Sunday. So that's homework 6. So even though it is numbered later, it is due sooner. And then you want to start learning the bold ions and acids. Now, I discovered when I was looking at our syllabus that we actually have a test next week on Wednesday. So pretty much up through section 3.2 is where we're going to finish for the quiz. But it is going to include these bold ions and acids and things. So hopefully you memorized the first set of polyatomic ions. There were many of you that it looked like hopefully that was just you hadn't gotten around to studying it. So you need to put in some time and effort, flashcards, whatever, to learn those before the exam next week. So any questions about upcoming stuff? Okay, so if you look at the board at the back on the left, I have a list of polyatomic ions there, starting with SO4 2-. So for the ones that I have given you the formula, I want you to talk to the people at your table, decide what you think the name of that ion is. And then for perchlorate and hydroxide, I want you to come up with the formula. Now, I'm just going to ask you to say the name, but I want you to put the formulas on the whiteboards at your table. So you can use 2 different whiteboards and put perchlorate in one and hydroxide on the other. Just to kind of check over, these are the ions you should have already memorized. Now, if you don't have them memorized, feel free to pull out that sheet that I gave you and start looking at that again to make sure that you're starting to pay attention to those. And I'm going to come around and pick up your surveys. So let's take a look at the ions here. The SO4 2-. What is the name of that ion?
Sulfate.
Sulfate. Okay. The CO3 2-. What is that one? Carbonate. And the CH3COO1- also is sometimes written with the carbons combined, and that is C2H3O2-. You might have memorized it one way or the other.
Acetate.
That is acetate. Very good. Okay. So if you have on your board perchlorate, what does perchlorate look like? That's right. Just show me your board. There you go. Okay, so chlorine, when it is a monoatomic, is a -1, but its oxo ions are also -1. So no matter how many oxygens you add, it stays as a -1. So in this case, ClO4 -1, you can put -1, 1-. There's a slight difference in meaning. I don't care which way you put it. Hydroxide. So I saw some of these as I was looking at the others. Yes, yes, yes. This one's pretty important because this is what makes a base, and we will use sodium hydroxide in lab a whole bunch. So for those of you that have lab, yes, that is going to be important to know. So moving over, I have some covalent compounds. Now, our ions look like covalent compounds. And when we go over the quiz, there were several people who were naming the ions as if they were covalent compounds. I can always tell it's an ion because it's going to have what? That would be an ionic compound, but a polyatomic ion is going to have a charge, right? So if it's an anion, there might not be a metal. An ionic compound would have a metal. But if there's a charge, I've got to use my memorized rules. That there's not really like a systematic way we can name them other than we start with the first element, and then if there's oxygen, we usually add either H or I. But you can't really tell how many oxygens there are just from the name. You have to memorize it. Now for the covalent compounds, there's no charge on them, so we're going to use our systematic rules. Now there are some compounds that have familiar names, but for this class, I want you to use the systematic rules. So for example, you may have heard of the compound nitrous, which is short for nitrous oxide. We're not going to use nitrous. We're going to use the systematic naming rules that tell us how many nitrogens, how many oxygens. Okay, so silicon is not a nonmetal. What kind of an element is silicon? We find it second row down. Metalloid or a semi-metal. So if we see a semi-metal, one of those ones in the brown, we are going to use the covalent naming rules. Okay, I will avoid putting those on tests and quizzes, but it may show up in your homework. So if you see arsenic or if you see Te, which is tellurium, then you would use the covalent naming rules. Okay. So what are we going to do with the numbers? Are we going to use Roman numerals or are we going to use prefixes? All I heard was mumble. Got to be louder. Prefixes. Okay, so Roman numerals go for ionic. Prefixes go for covalent when there's no metals in sight. Okay, so let's go to the second one, Cl2O7. How would we name that one? Dichlorine, 2 chlorines, hepta for the 7, but we drop the A, so hept oxide. Now, if you leave the A in there, I'm not going to count it off. Sometimes people actually say it with the A in there. I sometimes say it with the A in there. I'm not that nitpicky, but hepta is what we use for 7. Now, you may have thought, oh, I thought 7 was septa. There are Greek prefixes and there are Latin prefixes. I never remember which one is which, but we use the ones with the H's. So hepta and hexa instead of septa and sexa. So that's, just got to remember to use the H's. Okay, so on your board, with the agreement of the people at your table, what is the formula for tetraphosphorus decoxide? And then hold it up once you have it on your board. Yes, 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 yes. We agreed? Yes. Okay. So the 4 uses the prefix tetra. If you've heard of the game Tetris, they have like the blocks that come down. Each shape has 4 squares in it. So that's why they call it Tetris, is there are 4 squares making up each shape. So that's kind of how that one sticks with me for tetra. Okay. So before we go on to naming acids, I want to take a look at your quiz. I know that many of you are not happy with your quiz results. And to that, I say, How do I, oh, there it is. I will drop one quiz. So if you don't like your quiz score, we'll just do better on all the other quizzes and we'll be okay. So don't panic over this. But use this as a learning environment so that you can say, okay, I clearly didn't study my ions well enough, or maybe I need to pay more attention to where the metalloids are on the periodic table so that we can learn from the quiz and do better on that exam next week. Okay, so I'm going to go through the quiz. However, when I passed out the quizzes, I had some of the quizzes from my first class, section B in here. So if you look at the top and there is a letter B next to quiz 1, these answers aren't going to make a whole lot of sense. So I'm going to try and remember what the questions were so that I can do those with you as well. But I may have to ask you what the question is. All right, so I think, oh, I need to turn on the screen. Okay, so for our first question, most of you had phosphate. So of course it's going to have phosphorus. If you see 8, there should be some number of oxygens. Okay, so if you managed to get this far, you should have at least gotten partial credit. Phosphate has 4 oxygens and has a -3 charge. Now, if you have the word nitrate, again, you start with that element, nitrogen, ending in 8 tells us there are a certain number of oxygens. In this case, only 3 of them, and it's a -1 charge. Okay. This one, a lot of people tried to name using some of our systematic rules. If you see a charge, that means we have to go to the list of memorized names. So this one is carbonate. The element, and then change the ending to 8. What was number 2 for those of you who had B? Okay, and that's what we just did, which is perchlorate. Okay. For potassium fluoride, we've got K for potassium. So don't just assume it's going to be the first letter. If you think that's P, look on the periodic table and make sure. And you'll see that if we pull out the periodic table, P is actually phosphorus. So we need to go looking some more for our potassium. Okay. And then fluoride. And then we need to double check the charges. So potassium is +1. How do I know that? In group 1, right? And everything in that first group is +1. Fluoride is -1. And again, everything in that column, column 17, is going to be -1. So do those cancel out? Yeah. And I think the other one was calcium chloride. Is that right? So for that one, we have Ca and Cl. Will these charges cancel out? What's the charge on calcium? +2. And this one's also -1. So we need 2 chlorines to make that. Okay. All right. So you all had this structure. The molecular formula just tells me how many of each type of atom do I have. So you can start with any element that you want. You might say, oh, let's do the hydrogens. I see those first. So I'm going to count 1, 2, 3, and then over here 4. H4. C12, O2. That's a molecular formula. Okay. Now the other quiz had something that looks like this ring. So what would we do for the formula for this one?
first.
Okay, sure, we can do the H's first. How many H's are there?
6.
6. Let's do B next.
3.
3,
Then 3 for N.
and then
I think
3
that's
for
N, right?
Yeah, that's N.
Okay.
So we can also do those in different orders. So if you said B3, N3, H6, that would be fine. Same over here. If you said C2, H4, O2, that'd be fine. I think a bunch of you were thinking about the ion that you memorized, the acetate. So a bunch of you gave me a 3 for the hydrogen, but acetic acid has an extra hydrogen on it. So it's a little bit different. So some of you missed that. Okay. A lot of people forgot what an empirical formula was. This is just the lowest ratio, okay? So since all of these are even, the lowest ratio would be something like H2CO or COH2. Is there 6 different ways I could organize that? Up here, how many H's would I put? 2, because I can divide everything by 3, and then Bn. Okay. All right. Table salt, rock salt, sea salt all have the same formula, NaCl. Since it's wherever it comes from, it has the same formula. That means the ratio or proportion between the elements is the same. So if I look here, I see definite proportions. So that is B. Okay. Who is credited with the discovery of the nucleus? That Rutherford, A.
Rutherford. Okay.
Yes.
Because, yeah, you said Dalton, I was like, that's what I answered.
Okay. Thomson did the electron,
Okay.
and I think that was what I gave for section B. And then Millikan did the oil. I think everybody might have had this one, or you might have, no, the other class had it. So which part says the definite proportions? So definite proportions talks about a compound. So notice right here, I've underlined the word compounds. This is what talks about the ratio of elements in compounds. So this one's C. The other classes had the law of conservation of mass. Conservation laws say we're not creating this thing, we're not destroying this thing. So a lot of people went to this first part where they said we can't destroy the atoms, but this doesn't talk about not being able to make them. So down here at the bottom, it says in a chemical reaction, which is what conservation of mass says, is in a chemical reaction, we don't change mass. It is neither created nor destroyed. Okay. So if I were to ask this about conservation of mass, that's the one. All right. The atomic number is A, protons. If you had the mass number, that would be B. And if you had the charge, that would be D. We use this in the next one. Okay. So this says, which positive ion has 27 electrons? We're going to plug in these numbers into this formula here. So all of these have a +2 charge. So we're going to say +2, which is the charge, is equal to protons, which we don't know, minus 27 electrons. So now it's just a little algebra problem. Do one to one side as we do one to the other. So we're going to add 27. And so this says I have 29 protons. Okay. Did you guys have 3+ ions or 2+ ions? 3+. So I think that one was 3+ was equal to protons minus 21. Okay, so it had, if I said 21 electrons and all the choices had a 3+, then I would add 21 to both sides. And I would have protons equal to 24. Well, if I know that this is 29, how am I going to relate that to an element?
Find the atomic number on the periodic table.
Right. So I'm going to go to my periodic table and I'm going to say 29 is copper. And so that's the choice I picked. If I, in the other class, their number was 24, then I would go to chromium. Okay. I will put something like this on the test. So that's why I walked you through all of them. So in this case, it was B. Questions on this side? Okay. On the other side, I think people had the most trouble with bronze. So bronze is a mixture of metals. And so a mixture of metals is going to be a homogeneous solution. So how do I know it's a mixture? Because bronze isn't one of the elements on the periodic table. So if it's a metal, it's either an element or a solution, one of those two. If I can't find it on the periodic table, it's a solution. Same thing for steel. So if you had steel, that also is a solution. Helium, I think everybody got that was an element. And then the mineral calcite, CaCO3. So this has a chemical formula. If it has a chemical formula, that tells you that it's a compound or an element, but an element would only have one element. So that's not. If you had sucrose, sucrose had a chemical formula, and so that also is a compound. Questions on those? Okay. Most people did fine on most of this. One thing that threw some people was aluminum is a metal. So it is near that staircase line. It's a very weak metal, but it is still considered a metal. So if you look on our colored periodic tables, it is in dark blue. It's not in brown. So only the ones that are in that brownish orange color are considered semimetals. If you are colorblind and can't tell the difference on those, then ask me or let me know, and I'll make sure that I have a periodic table that the shading is something that you can see. You got bonus points if you remembered aluminum is 3+, and its mass you just look up on the periodic table. Chlorine, because it is in that second to last column, is a -1, and it is a non-metal. All right, how many neutrons does an atom of aluminum 29 have? Now, this 29 is that atomic number. We know the atomic number is equal to protons plus neutrons. Okay, so 29 is equal to 13, because aluminum is element 13, plus neutrons. So when I subtract that, I'm going to get 16. So I had a bunch of people that just looked at the mass on the periodic table and tried to figure it out from there. So remember that for an isotope, it's specific to that particular atom. We're not going to look at the periodic table. We're going to look at what's going on with that one atom. We're not rounding a mass. We're counting up protons and neutrons. All right. The isotope symbol for this element, 20 protons, tells us that it is calcium. To find the top number here, I'm going to add 20 plus 28. And again, we're not looking at the periodic table. We're adding 20 plus 28. So that's why there's a 48 there. And then since I have the same number of protons and electrons, that should be 0. So this commonly forms a +2 charge, but this particular atom has an equal number, so it is neutral. You could have left that off if you wanted, that is fine. And then I think the other class had magnesium, but yours was charged, so it should look like that. Okay. Questions? Next. So now we are going to look at naming acids. And we're going to use systematic names. We're not going to call them George or Susie or anything. So the first thing we have to do is recognize when we are looking at an acid. I'm going to put this right here. I hope this doesn't weigh too much. There are inorganic acids and there are organic acids. So organic acids are going to have carbon in them. So when we looked at acetate before, that had CH3COO, I can turn that into acetic acid by putting a hydrogen on it. So it has carbons in it. We're not going to worry about those right now, but their naming rules are going to be pretty easy when we do talk about them. Inorganic acids come in two flavors. We have binary, which has two elements. Now notice this starts with a hydrogen. So an acid has a hydrogen in it that when this acid is dissolved in water, it can become detached. So for inorganic acids, we always start with the H. So if you see an H at the front of a chemical formula, there's a pretty good chance that's some kind of an acid. So in binary, it's just the hydrogen and some other element. Now we might have more than one hydrogen, so it kind of depends on the charge of the ion. And then I said the hydrogen comes off in water. So we put AQ to indicate that it's dissolved in water. Now on your polyatomic ion list, we also have the gases listed. So if it were, so we're going to do the example HCl. If I had just HCl and then a gas, we basically use the naming rules we use for nonmetals, okay? We leave out all monos, but otherwise we use the naming rules for nonmetals. Whenever I'm talking about an acid, it's going to be an acid. It's going to be dissolved in water. So even if I don't put AQ, I want the acid name, okay? So our basic rule here is we're going to put hydro at the front and then the name of the element, but instead of "ide," we're going to change the ending to "ic." And then we're going to add the word acid. So using this logic, HCl would be hydro, and then we have chlorine, so we would put chlor, but instead of chlorine or chloride, we would say chloric, and then tack on the word acid. Hydrochloric acid. Yes?
Okay. All right, let's write stuff down. So you put hydro on if there's an H.
You put hydro on if there's an H and only one other element.
Okay.
Okay, those are called binary acids. Okay, so if you've had a chemistry lab before, you've probably worked with hydrochloric acid. I don't think we've used hydrochloric acid in our labs yet, but we will in a few weeks be using that in several of our different labs. So hydrochloric acid is coming up all through October. We're all about hydrochloric acid. So this is a good one to know because you're going to see a lot of it if you have labs. Okay, like I said, it doesn't have to be just one H. So I could have H2S because sulfide has a -2 charge. All right, so I'm going to say hydro, sulfuric, acid. Now we do have a polyatomic ion that doesn't have oxygen in it, but it's also not going to make a binary acid. So HCN is where a hydrogen combines with the Cn-. What is Cn-? Cyanide. This follows the same naming rules. So we would say hydro, cyan, but instead of I, cyanic acid. Okay, and I saw a hand somewhere. Okay, so that's binary. Oxo acids start with an H, then some element, and then they have oxygen. Now that element is usually a nonmetal, but it doesn't have to be. We will mostly stick with the ones that it's a nonmetal. So they're going to look very similar to the ones up here, except for they've got oxygens at the end. These all come from the oxo anions that we started with. So our oxo anions end in ate or ite. If it ends in ate, like most of the ones we've looked at, sulfate, perchlorate, carbonate, we're going to change that to ic. And then we're going to add the word acid. Okay. So very similar to what's going on up here, except we don't start with hydro. We just use whatever the anion name is, change the ending to ic, and then add the word acid. If the ending is ite, that means there are fewer oxygens, but there are still oxygens there. We change that ending to us. O-U-S, not just U-S. And also add acid. Okay, so let me go through a couple of examples. So if I take the ClO4 that we were looking at before and stick an H on the beginning, I'm going to take this ion, which I recognize as perchlorate. I'm going to start writing it, perchlor. But instead of 8, what am I going to write? Ic.
Acid.
And then acid. Okay, so notice there's no hydro here. So if there's oxygen, I leave off hydro. If I have H2SO4, and again, because this is a 2- charge, we need 2 hydrogens to balance it. What was SO4? Sulfate. So I'm going to call this sulfuric acid. This is another very important acid. It is battery acid, but it's also one we use in lab from time to time. Not as often as hydrochloric, but it's pretty important. So it's good to know this formula. Now, sulfate has a very similar ion, sulfite. Okay, that has 1 less oxygen. So H2SO3, I look and say, oh, SO3, that is sulfite. Right? So now I'm going to changing sulfite to sulfurous. Okay. Yes.
Yeah. Like I said, I to us, but there's also an R.
Okay. So almost all of the elements, you're just changing the ending. So if I had nitrate, it would be nitrate. Nitrite would be nitrous. If I have chlorite, it would become chlorus. Sulfur has to be weird, so that's why I kind of pointed out. This one goes back to its original full name, only in acid form. In ion form, we just have the sulf part, but in acid form, here it's sulfuric acid, and then over here it was hydrosulfuric acid. So for some reason, people that be have decided that we don't shorten sulfur, we use the whole word sulfur. Okay, so that is naming ions. Okay, I only have 6 minutes left. I want to get through some of the stuff that's going to be in lab, so let's switch over to that. Okay, so we talked on Friday about how we can find the molar mass or formula mass of a compound or an element, right? So this has 2 oxygens, so we add together 16 and 16, and that gives us the 32. So that tells us that 1 mole of oxygen weighs 32 grams. But what if I don't have a 1 mole? What if I had 64 grams? Could I tell how many moles that was? 2, okay? And so you can figure that out because you can see that 32 times 2 is 64. So that's pretty easy to do because you can recognize doubles without too much trouble. Normally, we're working with less than a gram in lab, so we don't have even one whole mole, okay? So we need a way to get to moles without having to figure out about doubling and whatnot. So we're going to start with a measured amount, and so that means grams or moles or milliliters. You wouldn't use density, that's not a measured amount. In this case, grams. And we are going to multiply that by what's called a factor, which is a fraction with a conversion ratio. So if you've ever heard of dimensional analysis, unit analysis, factor label dimensional analysis, this is what that is, okay? So that fraction is going to have the ratio of the units that we have, grams, to the units that we want, moles. And fortunately, we've just found a molar mass, which is that very ratio, right? But we can use that ratio the way we normally think about it or flipped upside down. So what we do, start with our 64, and then we'll multiply by a fraction. We put the units that we don't want, the ones we're trying to get rid of, and we put those on the bottom. So grams goes on bottom, and the units we do want on top. Moles. Okay. Then my molar mass is 32 grams per mole. So that means 1 mole weighs 32 grams. You've got to pay attention to where you're putting your numbers. Okay. This number goes with the unit gram. So wherever grams goes, that's where that number has to go. Then I remember my rules for multiplying by fractions. I'm going to multiply all the top numbers and divide by the bottom numbers. So basically I'm saying 64 divided by 32, and that's going to give me 2. Okay, so that's how we're going to get to moles. Now in lab, you are trying to find an empirical formula. So that's the ratio between parts of the compound. You are going to have a salt. It's called Epsom salt, but that's just a common name for magnesium sulfate. I'm going to do an example with a different salt. So salt just means an ionic compound. I'm going to simplify this and say we have the anhydrous barium chloride, and that weighs get my numbers out here. While I'm looking for this, anhydrous means without water. So this is when it's already been dried off. 1.982. Okay. The water we find by weighing our compound ahead of time, heating it up until all the water goes away, and then seeing what the difference in mass is. And so we measured this to be 0.343. So our method for figuring out the ratio is going to be these 3 steps. Oops. We're going to find the molar mass of each part. We're going to convert each of those masses to moles, and then we're going to divide by the larger number. Now, Bennett, you had a question? No, I thought I saw you raise your hand. Okay, so we already found last week that water was 18.02 grams per mole. So using that same method as above, we would take the 0.343 grams times a fraction with grams on the bottom, moles on top, with the 1802 on the bottom, and when we plug that in, we're going to end up with 0.0190 moles, okay? Because we're like right out of time, I'm just gonna jump ahead. This has a mass of about 208. I'll let you calculate that. We end up with 0.009 moles. Okay. And then we divide the larger number by the small. That's so we can get a whole number. Which is larger, the 0.3 or the 0.009?
3.
0.3. Oh, wait, I'm sorry, not the 0.3, the 0.019 or the 0.009. The 1. So we would divide 0.010 by 0.009518, and we end up with right about 2. Okay. In your lab, it's not going to be 2 because you're working with a different salt. Okay. So you're going to round to the nearest whole number for that. I know that was fast. I did slow down my explanation in the video that I sent out. So if you haven't taken a look at that and this seems like too much, go back and look at that video. I went through it more slowly. Okay. See you all on Friday.